actually did some theory. Then, so let me answer you in the following way. Because it's so difficult to put a magnet in space, the magnet in space will always rotate. And so if you're not careful, your space shuttle, space station will lose control. Our first flight proved you can actually put a magnet in space. Now, with such a large magnet, with such a precision instrument, if at the edge of observable universe, if there are equal amount of antimatter, there will be order 10 to 20 arriving on the in AMS. If you expect 10 or 20 anti-helium or anti-carbon, and if you didn't see one, something is wrong. And the interpretation is difficult to say. Okay. Because the reason antimatter, we do not see antimatter, has never been found. There are many theories and predict many results, but none of them has been correct. Have I answered you?
Is there a time you would expect, if you're seeing 10, 20 antiheliums, in other words, as a science writer, how soon should I expect you guys to be up here or at headquarters saying we found something?
Oh, I have advised my colleagues. Right? It took us many years to build this thing, right? And there are multi-redundancies. By any standard, it's an extremely precise, accurate detector, and we have calibrated detector over again in test beam, in accelerators. And so we are going to do this very slowly. Carefully check everything. And we're going to form 2 analysis groups to check each other. And so we're not going to publish preliminary results and confuse everyone. So we're going to do it very, very carefully. Fortunately for us, perhaps we don't have any competition. So we're going to do it carefully on our own, and but do it right. So I'm not able to tell you how long it will be.
Aye, in the front row here.
Jim Siegel, Celebration Independent Newspaper. I have a two-part question for Mr. Gonzalez. First of all, I'm curious as to why the Department of Energy is involved in this project, in fact leading it, as opposed to some other agency of the United States government or some other entity. And secondly, given what Professor Ting told us a couple of weeks ago during a briefing about the amount of energy that is potentially contained in cosmic rays, whether you would expect it possible that a discovery from the AMS may result in some significant find that would help the energy supply of the United States or of the world.
So the second one I'll take first. And I think as a scientist I would say never. But the details I will leave for Professor Ting to answer. And the first one, why DOE? We have an Office of Science within DOE, and that office is the single largest funding agency for physical sciences in the U.S. and has a broad portfolio, and part of it is fundamental research, which is where high energy physics, the office I'm in, falls into. And this AMS, what it does, the goals of AMS, that science mission, just falls perfectly with what we do. We have a number of national labs in the U.S. that are trying to address the same question in different ways, and using accelerators. And we fund research at the LHC at CERN, for example, which also tries to address this question. So I think the answer is that's what we do.
Okay, we'll take a couple of questions on this side of the room before we come back over here.
Mark Boucher, Space Ref for Professor Ting. Can you characterize the differences and capabilities between AMS, which flew on STS-91, and AMS-2?
Oh, first of all, AMS-1 flew for 10 days. AMS-02 will last the duration of space station. That's number one. Number two, AMS-1 has 4 type of detector, and AMS-2 has 7 very precise detector. The size and scope and the precision are totally different. In AMS-1, we just do the proof of principle. In AMS-2, what we have decided to do is to do as precise, as accurate as we can manage it. We try to push the envelope to the limit.
My question's for Dr. Ting. My name's Randy Atwood, Sky News Magazine. Just a follow-on to the previous question. Were there any lessons learned during the first AMS flight that changed your thoughts on the design for AMS-2?
No, sir. AMS-01 just showed everything worked. We published a few papers, extremely interesting papers, and nothing learned, just except everything worked.
Back over on the other side of the room.
Hi, I'm Alan Boyle with MSNBC. For Dr. Ting, before the startup of the LHC, there was a lot of talk about strange phenomena that might happen, creation of black holes, creation of strangelets. Do you think that the AMS experiment will shed light on those nightmares that people used to have? Because a lot of physicists said at that time, well, if these phenomena occurred, they would be occurring out in space, and we would have cosmic signs of that. What sort of cosmic signs do you think AMS would produce, either to kind of still any sorts of worries about nightmares or shed more light on strangelet phenomena?
I do not know how to answer these philosophical questions. Our only nightmare for AMS during the 17 years was to be removed from the manifest. That was indeed a nightmare. But to the credit of DOE, to the credit of NASA, to the credit of my senior collaborators from different countries, everybody realized this is such an important experiment. Even when we were off the manifest, nobody stopped us. Nobody stopped funding us. We still continue. That's the only nightmare I had.
Go ahead.
This is Mark Ratterman from Talking Space. Professor Ting, I bring you a question from a science advisor for our show, Catherine Qualtrough, and her question is about some recent events. The RHIC, the Relativistic Heavy Ion Collider at Brookhaven National Laboratory, has recently reported the first ever observation of the antimatter helium nucleus, antihelium as you've called it. Can you address the importance of this find and how it relates to the goals of AMS?
They are not related at all. Right? Antihelium, the helium is 2 protons, 2 neutrons. Right? And it has an isotope called helium-3, 2 protons, 1 neutron. Both has been observed, but should have been observed. Right? The question is, the hidden question, the important question you ask is, could nuclear collision in space produce this? Okay? And the rate, what they observe is so low. Okay? In space, from cosmic ray collision, will not produce this. That's number one. Number two, if we see antihelium, we should also see anti-carbon and other nuclei. And these cannot be produced by accelerators on the ground because the mass is so large. So it's interesting, right? But really had nothing to do with us.
Ken Kramer.
Hi, Ken Kramer for Spaceflight Magazine. Professor Ting, as a scientist, you're probably thinking maybe a little bit about the next experiment. What would you like to do beyond this? Thank you.
I think probably Professor Scher, Professor Battistone, and academician Lee can answer these questions. And for me, if you look my career history, I have always do one experiment at a time, because I always view my ability is limited. Okay, we have just started, as Mark just pointed out. Okay, this is the first step. This experiment will last 10 to 20 years, and so probably it's a little bit too early for me to think about the next experiment. But there are different kind of people. Many people are much more gifted than me. They can do 4 or 5 things at the same time, and I'm very limited. Only one thing very slowly after another. But I don't let it go. I want to understand everything.
Clara.
Clara Moskowitz with Space.com, and this is a question for each of the participants. If you could just address what you felt when the experiment was taken off the manifest, and if you had personally given up hope that it would ever get to fly.
You're asking whom?
Let's start with you.
Ask me. I was very surprised. I was very surprised, but to the credit of people in NASA headquarters, okay, in Johnson Space Center, even who were off the manifest, the key support from the Mission Management Office continue to support us. And the Department of Energy has a thorough review by some of the best scientists in the United States. And they advised DOE, this is such an important thing, we should carry on. Right? And similarly, the French, the German, the Italian, the Swiss, the Taiwanese, the Spanish, all decided to carry it on, even though whom had no flight. You have to understand, I have no financial authority over any of my senior colleagues. People join this because they found the physics is compelling. And that's why we managed to finish. So I would say surprised is the most polite word I can think of.
I think from the DOE perspective, clearly we never gave up hope, and just because the science was so compelling, and that's what we focused on keeping the experiment going, the collaboration going, and yeah, we certainly didn't give up hope. We were very concerned at times, but things worked out. So we're just very happy to be here today.
Well, on behalf of NASA, I would have to share both Sam's and Saul's comments. I think the flip side of that coin, to answer your question, it's important to also note who was responsible for helping us get our flight back. And unfortunately, not present here today is William Gerstermeyer, the Associate Administrator at NASA for all human spaceflight. Certainly, among us, I would have to say that we owe a tremendous amount of debt